Well, hello everybody. Sorry for the delay there. I've been trying to get this up and running. The computer crashed and did not want to start back up, so I had some work to do to try to frantically get on in time for class. So, now that I'm finally here, I'll give you guys a couple minutes to make sure that you get in. Anyway, sorry. What we're going to be talking about today is we're going to be talking about isomorphism. So what does that mean? Well, we will get to that. And so what I'll try to do is try to explain what the question is. Sorry, the PowerPoint got cut off a little bit at the bottom. I was trying to fix that when my computer crashed. So if the PowerPoint is a little weird today, I'm apologizing for that ahead of time. But the question is, if I write the integers, notice that I can write the integers as 1, 2, 3, 4, 5, 6, 0, -1, -2, and so on. Or I could use Roman numerals and write 1 or I, Wow, that sounded terrible. I would never want to use Roman numerals. But I could also write out the words 1, 2, 3, 4, 5, or 0, -1. Or if I wanted to do this in Spanish, I could go 1, 2, 3, 4, 5, 6, and so on. Now, the point I'm trying to make here is that I have the integers for each one of these. They're each representing the integers, but I'm using different names. So I'm doing a renaming. And if I look at the integers under addition, well, I would think if 1 plus 2 is 3, then 1 plus 2 is 3. Or I plus I is I. So regardless of the notation we're using, the numbers are still behaving the same. Even if I were to relabel 1, 2, 3 as alpha, beta, gamma, it really doesn't matter what I label them as, they still behave the same way. So as such, with each of these namings, I would consider each of these to be equivalent to the set of integers. So the point here is that, well, how can we have the set of integers and not always just use 1, 2, 3, 4, 5? How can we use different names? And if we do, how do we determine if those things are the same? And that's the basic idea that we're going to be exploring today is what does it mean for two things to be the same up to a renaming? Alright. So in order to get there, what we're going to have first is I'm going to define a homomorphism. So if I have a mapping from G to H, and we've talked about mappings, remember G would be the domain, H is the codomain, and therefore we'd have that mapping from G to H means everything in G gets mapped to exactly one thing in H. Alright, now a homomorphism is a mapping, but on top of that it also has the property that if I take alpha of A times B, where times is the operation for G, and my hashtag there, or my sharp sign, I always think it's a sharp sign. It's from reading sheet music too much. Anyway, if I do that before or after taking theta, it's going to be the same. So that is, I would say that theta respects the operation. So theta of AB is equal to theta of A times theta of B. So actually I'm going to stop there and draw a picture to try to say, well, what does that mean? What would that look like? And that kind of thing. Sorry, I don't think I started Discord, so I'm trying to do that real quick. Alright, well, I cannot get Discord started, so if you would like to talk, please write in chat on YouTube so that I can actually answer your question. Um, might have to go out and buy a new computer. That would be such a horrible thing. Paula, if you're watching this. Anyway, moving on to my question. All right, so what we have here is we have G and we have H. So here's G and here's H. The idea behind the mapping is that I might have an A here, and that through my mapping theta, I'm going to go from A to, let's say, C. And B is going to get mapped to D. So if I look at this picture, okay, theta is going to map A to C, B to D. That's just what it means to be a mapping, is each one of these goes to exactly one of these. What it means to be a homomorphism is the idea is that, well, if I take A times B, because G is a group where my star is my operation on G. Now, the reason why the operations can be different is one of these could be using multiplication, one could be using addition, one could be addition mod something, one could be something else entirely. So they don't necessarily have to have the same described operation, it just has to behave the same. And the idea is if I take A times B, this is going to get mapped to C times D. So if I know I have A and I have B, if I map A to C and B to D, or if I find A times B, it's going to be mapped to the same as C to D. All right, to write this another way, as here I could have A and B, and so I can map, say, A to, from G to H, and this gets mapped to C, and so I could do this. And then I could say, okay, well, I could do that, and I can map to C, and I can map from B to D, and now if I multiply these two, so I multiply together, I would get the same thing, the same answer, as if I had multiplied first, and then used the mapping. So I can do the mapping, and then multiply, or I can multiply and then do the mapping, and I end up with the same thing. So I get a picture like that. All right, to be precise, I can have this picture commutes. So here I'm taking multiplication. Here I'm taking the thing in H. And then here I have theta and theta. So that is if I map under theta and then I multiply, this is the same thing as multiplying and then mapping under theta. And so I have a commutative diagram here is what I would say. All right. You know what, T? I have a gaming computer, and it's only 2 years old. So I am really upset that it's broken, or that I'm having these troubles at all. So I'm going to have to buy a new, better, more expensive gaming computer that won't break on me, hopefully. I honestly don't know what's going on, though. It's just having a lot of issues. All right. Back to our lecture, though. That would be a homomorphism. Now, to point out that the next thing I would say is that I have an isomorphism if the homomorphism is also one-to-one and onto. So if I have a bijective mapping, which also respects the multiplication or the operation on a set, then we would say that it is an isomorphism. And now what I claim is that if G and H are essentially the same up to renaming, if and only if they are isomorphic to each other. So if there exists an isomorphism from G to H, then we say that, and then down here at the bottom right, I use that sign, an equal with the tilde above it. So G is isomorphic to H. And if that's the case, then really G and H act exactly the same way. They have the same elements up to a renaming, and the operation acts the same way up to a renaming. And so if we want to determine if two things are the same, that's what we mean in abstract algebra, or algebra in general, is that two groups are the same if there exists an isomorphism from one to the other. All right. So just for some examples here, so we can work through this. What I'm going to have is, let's let theta be from the cyclic group generated by 1, 2, 3, and I'm going to map that to Z3, and I'm given that by theta of the identity mapping is 0, theta of 1, 2, 3 is 1, and theta of 1, 3, 2 is 2. What I want to do is I want to show this as an isomorphism. Alright. So what I need is, in order to show that theta is an isomorphism, I have to show that theta is a well-defined mapping first. So if I start off with something in the cyclic group generated by 1, 2, 3, remember that we found this actually on Monday was the set consisting of the identity mapping, the mapping 1, 2, 3, and the mapping 1, 3, 2. Now, in order to show it's a well-defined mapping, I have to show theta sends each of these things to exactly 1 point. But I define theta just as theta of 1 is 0, theta of 1, 2, 3 is 1, and theta of 1, 3, 2 is 2 in Z3. So the idea is that, well, if this is mapped to 0, this is mapped to 1, and this is mapped to 2, then everything is mapped to exactly one object. Therefore, it is a well-defined mapping. To check onto, notice that we map to 0, 1, and 2, and since Z3 is equal to the set 0, 1, and 2, we are indeed an onto mapping. So now, a lot of times we define these mappings and we use some type of rule to say what it's going to be in general, but because I've actually just listed what each of the images are, or where everything gets mapped to, I really am just checking to say, is it onto? I have a 0, I have a 1, and I have a 2. That is Z3, so it is onto. Is it 1 to 1? Do any of these things go to the same thing? No, they do not. So this is also 1 to 1 mapping. So this is a well-defined 1 to 1 onto mapping. The last thing we need to do is we need to show that this is an isomorphism, so we have to show it's a homomorphism. So to show it's a homomorphism, we have to show it respects the multiplication. So what we have to do is show if I take A and B in the group generated by 1, 2, 3, then theta of A composed with B is equal to theta of A plus theta of B. Now I'm using these because in the group generated by 1, 2, 3, I'm using composition, whereas in Z3 I'm using addition modulo 3. So I have to show that for any two A and B in here, I have to get this. All right. Now, most of the time, again, we would do this by checking some property and showing that that has to be true. But because this is a small example and I define things succinctly, or by actually giving what their images are, I'm actually going to have to check for every pair. So if I want to check every pair, I have to think, well, not just any two at a time, but I can repeat as well. So there'd be 9 different options I have to check. So 0, 0, 0, 1, 0, 2. 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. And so I'm really just going to make a list and kind of see what happens there. So if I find 1 composed with 1, 2, 3, and then I take theta of that, I get theta of 1, 2, 3, because the composition is just 1, 2, 3, which is 1. But I do want to point out that 1 is 0 plus 1 is equal to theta of 1 plus theta of 1, 2, 3. So that's what I mean by checking these are the same, is that if I find theta of 1 plus theta of 1, 2, 3, that's 0 plus 1, which is 1. On the other hand, if I compose on the inside, I get theta of 1, 2, 3, which is just 1. So in both ways, I get the same thing. Now, if instead of using a 1, 2, 3 here, if I said theta of 1 composed with anything, what I get is the identity composed with anything is that anything. But if I find theta of 1 plus theta of that anything, notice I'm going to get 0 plus theta of that thing. So actually, instead of having to go through all cases, I could just say, well, if I start with the identity, then the identity composed with another one of the mappings is just the mapping. So if I map this under here, I get the image of A. But if I do theta of 1 plus theta of A, I get 0 plus theta of A. Since 0 is the identity for addition, I get theta of A. So if one of my numbers is 0, I know that this is going to respect the operation. So far it's satisfying being a homomorphism. If I change the ordering, this also works. So if I say A composed with 1, and that is important, I do have to do both directions as well. Then I get theta of 1, A plus theta of 1 is what I want to be equal to, but this is theta of A plus 0. And notice I'm working for both ends. I want to show this is equal to this, so I said this is equal to this, and this is equal to this. Okay, now they're clearly equal. So as long as I have one of them being the identity, I have to get that this is the case. So let's suppose none of them are the identity. So I have to try something like theta of 1, 2, 3 composed with 1, 2, 3. Now I want to show that's equal to theta of 1, 2, 3 plus theta of 1, 2, 3. Well, if I take 1, 2, 3 composed with 1, 2, 3, I get 1, 3, 2. So to get that, again, you should just go 1 goes to 2 goes to 3, 2 goes to 3 goes to 1, 3 goes to 1 goes to 2, and we do get 1, 3, 2. But we notice 1, 3, 2 is, the image of that is 2. However, if I work from the other end, the image of this is 1 plus 1, and 1 plus 1 is indeed 2. So we get for 1, 2, 3, 1, 2, 3, this works. So then I could try 1, 2, 3, 1, 3, 2. Well, if I compose those, I get the identity. So that's 0. But if I add these, I get 1 plus 2. And 1 plus 2 mod 3 is 0, so we get it works there. We'd also have to check 1, 3, 2, 1, 2, 3. But then we're going to get theta of the identity is 0. In this case, I'm going to get 2 plus 1 is also 0, so it works out there. And the last one I'd have to try is 1, 3, 2, 1, 3, 2, which is going to be 1, 2, 3. So I get 1. On the other hand, I get 2 plus 2. And notice 2 plus 2 is indeed 1 mod 3. So it wasn't a pretty proof, it was a brute force proof. I just went through and checked any two at a time, wrote out the composition, and then I found the image individually and added them together. And so whether I do the composition on the inside and then take the image, or if I take the image of each piece and then add them, I'm going to end up at exactly the same spot. So therefore this would be a homomorphism. Since it's also one-to-one and onto, this would be an isomorphism. So what we would say is that the group generated by 1, 2, 3 as a subset of S3 is isomorphic to Z3. So what that really means is despite the fact that these look drastically different, these are actually the same groups. They behave exactly the same. They both have 3 elements. I have an identity element, and I have 2 elements of order 3, where if I add each of these other 2 non-identity elements are each other's inverse, and so all of those properties still maintain. Anything that happens in here also happens in here. So these have exactly the same properties. The only difference is a renaming of the elements and of the operation. So even though they look different, they are the same. If you guys have any questions in there. Do you follow that those look to be the same? All right. All right. The next one I want to show is that if I map the integers to the set of even integers, where n is mapped to 2n, I also want to show that this is an isomorphism. So what that means is the integers is isomorphic to the set of multiples of 2 under addition. All right. Well, how are we going to do that is we're going to go through. Sorry, I went to the wrong screen there. And so we're going to have theta is a mapping from z to 2z, given by n is mapped to 2n. And I want to make sure that this is a well-defined homomorphism. And also one-to-one and onto. First off, I just want to check. If I take an integer and I multiply by 2, so I start with an integer, do I end up with a multiple of 2? Well, that seems pretty obvious, doesn't it? I take an integer and multiply by 2, I end up with an even integer. So, and I end up with one answer. Therefore, this is a well-defined mapping. Most of the time, if you recall back to that section, we're really just checking well-defined. We don't necessarily write out the proof, but we do want to say, if I start in the set of integers, I multiply by 2, I end up in the set of 2z, which is the multiples of 2. So it is a well-defined. Is it one-to-one? So what we can do is let the image of n1 equal the image of n2. So to show one-to-one, I have to show then that n1 is equal to n2. Well, if theta of n1 is 2n1 and theta of n2 is 2n2, so if 2n1 is equal to 2n2, n1 is equal to n2. So for one-to-one, we get that. We suppose that the images are the same. We show we had to start at the same point. Therefore, this is indeed a one-to-one mapping. Also for onto, we can say let y be into z. Then by definition, y is equal to 2k for some k and z, because 2z is the set of all the things that look like 2k for some k and z. Now, I know that k is an integer, so theta of k is equal to 2k is equal to y. Therefore, for every y in 2z, there is an integer k such that theta of k is equal to y. Therefore, we are indeed onto. So this is a well-defined one-to-one onto mapping. All right. And so those are reminiscent of proofs we've done before. What we have at the new part now is that we have to show this respects the addition. So what we want to show is we say let a and b be integers. What I need to do is I need to show that theta of a plus b is equal to theta of a plus theta of b. So that's what I need to show that it respects the operation. So that is theta of a plus b is indeed equal to theta of a plus theta of b. Well, what we're going to do is we're just going to calculate this. Theta of a plus b is, well, n is mapped to 2n, so this is 2a plus b. On the other hand, theta of a, again, I'm working both directions just to make myself life a little bit easier, is theta of a is 2a, theta of b is 2b, and so what I need to do is just say, can I get from 2 times a plus b to 2a plus 2b? Well, if I just use the distributivity of the real numbers, or of integers for that matter, I get, in fact, 2a plus b is 2a plus 2b is theta of a plus theta of b. So this mapping does indeed respect the addition on the set of integers or the set of multiples of 2. So this is an isomorphism. So that is z is isomorphic to 2z. So we can say these are both cyclic groups. This one's generated by 1. This one's generated by 2. So basically what I've done is I've renamed the integers. Instead of calling all the integers 1, 2, 3, 4, 5, 6, I've just renamed them 2, 4, 6, 8, 10, 12, 14. And by doing that renaming, notice that I don't actually change anything other than what I'm calling things. So if you wanted to write the integers as 02468, because I want different names for my stuff, well, they behave exactly the same as they otherwise would, so there's nothing wrong with that. Other than the fact that you should tell people you're doing it, because otherwise you're going to confuse them. Any questions on that one? Did you follow that proof? Just give me a heads up if you guys do have any questions along the way. I'll keep checking the chat here. I know I can't hear you in Discord, but at least I can check the chat and make sure that you're following along. Well, good. I'm glad it felt more straightforward. I like that one better than the first one because brute force proofs are always just kind of like do a bunch of stuff. It's nice when they're a little prettier. All right. So now this one got cut off a little bit too. I was going to break this up. I don't know why I didn't mean to put two theorems on the same slide. It just kind of happened. Anyway, what I do want to do though is I want to show that suppose that G is isomorphic to H and G is commutative. What I want to do is I want to prove that H is commutative. So we'll get to this other one later. But let's do that. I have two isomorphic groups, G and H. If G is if G is commutative, I want to show H is commutative. So what does that mean is let G be isomorphic to H and G be commutative. Then what I have to show is H is commutative. Now, just to point out, remember, commutative means that, so if let A and B be in G, then it just means that A times B is equal to B times A. So I can reverse the order of the operation. And because I have different groups here, I might have different operations. So I'm going to say A times with a little GB is B times a little GA. Now, you don't always have to do this if it's clear that you're talking about multiplication in G, but because I'm using two different groups, I'm just saying, okay, we're going to multiply in G, and then down here we're going to multiply in H. So I'm going to say if C and D in H, then C times D in H is equal to D times C in H. So if I use the multiplication in H, then C times D is D times C. If I use the multiplication in G, A times B is B times A. So this is what I get to assume. This is what I have to prove. All right. Now, the next thing I need, in order to get from here to here, I can't just directly do that. What I need to know is that these two are isomorphic. So what does that mean is there exists an isomorphism theta from G to H. Now, could be many isomorphisms, but I'm just going to say because they are isomorphic, there's at least one isomorphism. So I'm going to pick that isomorphism, and I'm going to say that, okay, theta is a mapping from G to H. It's going to be a well-defined mapping. It's one-to-one onto, and it respects the multiplication. So somehow I need to use this to get out that this is true. Well, how in the world can I do that? Well, what I need to note is that I'm just going to take C and H times D is equal to, and my goal is to get this out. So I'm going to erase this so that I have more room because I'm going to need it. So if I take C times D and H, what I know is that C is in H. Since theta was an isomorphism, that means that it's onto. Therefore, there exists something in G such that C is equal to theta of A. So that is, there exists an A in G such that theta of A is equal to C. So instead of writing C, I can just write theta of A. But if I do that for D, I get there exists a B in G such that theta of B is equal to C because theta has to be onto because it is an isomorphism. So instead of D, I can write theta of B. All right, so that's the first thing we needed is, well, what we wanted to do was take C times D, and I'm trying to use this isomorphism thing, so instead of C, I'm writing theta of A, and instead of D, I'm writing theta of B. Well, what I know is that this theta also respects the multiplication, so this becomes theta of A times theta of B should be theta of A times B. So we could do the multiplication after theta or before theta. So if I'm taking theta of A times theta of B, that's just theta of A times B, where that's is in G. Okay, that makes sense so far. I actually don't know where I'm going other than the fact that eventually I want D times H, or D times C in H. So now I'm just going to look at this and think about it and say, well, A times B, notice G is commutative, so that is the same as B times A. So that was given to me that G was commutative. I should probably use it. But now what I get is, well, if I go backwards from this direction, that is, instead of multiplying in G, I multiply in H, this is going to be theta of B times theta of A. So since theta respects the operation, theta of B times A is the same as theta of B times theta of A. But theta of B was D and theta of A was C. So in the end, we got C times D has to be D times C. So in fact, if I have a commutative group and it's isomorphic to another group, the second group also has to be commutative. So the fact that it respects the multiplication means that it will respect commutativity as well. Now, just to the point, that's the type of thing that we want to use isomorphisms for, is say, oh, well, if we have this isomorphism, what types of things are preserved and what types of things aren't? Well, the names don't have to be preserved, but things like commutativity have to be. Things like associativity would have to be, although they'd already be associative because they're both groups. But other things like that would have to be respected. And so, some other things that would have to be respected, or it'd have to be the same, is, well, I have some things listed down here, and what they say is, I know I'm kind of ran out of room there, but there's a couple properties. The first one I want to show is that the theta has to map the identity in G to the identity in H. So if I start with the identity, it has to be mapped to the identity. If I have theta of, and I find theta of A inverse, that is equal to theta of A inverse. And if I take theta of A to the K, that's equal to theta of A to the K. So I can take the inverse in G or the inverse in H. Either way, with theta, it's going to respect that. Or if I raise to the kth power, it's going to respect that. And so I want to show those properties. And as I walk through those, I'm actually going to start with number 3 because that's the easy one. The last bullet point I will write down for you so that you have it correctly. And we'll do that first. All I'm writing is theta of A to the K, where that's as in G, is equal to theta of A to the K, where to the K is as in H. Well, if I want to do theta of A to the K is equal to this, I'm going to start with this and I want to get out that. So if I'm multiplying A to the K is really just A times A times A times A, where we have a total of KAs. So that's what I'm saying. So if I multiply A by itself K times, whatever the operation is G K times with A itself, Well, notice that what happens here is that this is an element. So what I get is, because it respects the operation, this is theta of A times theta of A times A, where I have k minus 1a's. I can do that again, and I'm going to get theta of A times theta of A with k minus 2a's. And so eventually what I'm going to get is theta of A times theta of A times theta of A dot 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 times theta of A. And if I count these up correctly, there's exactly k of them. So the idea here is that if I want to raise something to the kth power, I can do that before or after the mapping, because theta of A to the k is the same as theta of A times itself k times. But because this respects the operation, I can turn this into theta of A times theta of A times theta of A, which is really just theta of A to the k. Now, that's going to be helpful at times, because we might do something like theta of, if we're working with the integers, theta of 8 is really just theta of 2 cubed. So if I know theta of 2, well, this is going to be theta of 2 cubed. So instead of finding theta of 8 directly, if we already know theta of 2, we can just take theta of 2 cubed and we'll get out theta of 8. And so sometimes it's easier to find the smaller ones and use those to build up the bigger ones. So this does become helpful as we're trying to find groups. All right. Now, what I want to show is that theta of the identity in G is equal to theta, or is equal to the identity in H. So, that is one element that we know has to be in the group, is it has to have an identity. Not only that, but for every isomorphism, we have to have that. The image of the identity is again the identity of the new group. So that's point 1. So let's go ahead and prove that. Now what I want to think about is, well, if I take H has to have an identity. And G has an identity, EG. So there have to be identities. Now in order to be an identity, that means that EH times X is equal to X times EH is equal to X for all X in H. So now I'm not going through the formal proof. I'm just writing out things I know. Okay, H has an identity, G has an identity. What it means to be an identity is that if I multiply by something on either side, I get out the original something. So if I want to show the image of EG is equal to the identity on H, what I really have to show is that the image of EG satisfies this property. So I have to show theta of EG times X is equal to X times theta of EG is equal to X for all X in H. So I haven't even started the proof. I'm just trying to think through what it even means. Well, what it means is that this will behave like an identity. Since the identity is unique, if I can show this behaves like an identity, it has to be the identity on H. So I have to show that this element commutes with every element of H and is always equal to X in both directions. So this is what I need to show. All right, I'm going to write that at the bottom so we have that as a reference. So X theta EG is equal to theta of EG times X is equal to X for X in H. All right, so if we're going to get there, what we should do is let X be in H, and we want to talk about what X theta of EG is equal to. Well, notice that x is in h and theta of EG. Well, EG is in G, so this is the image. So talking about these directly is difficult because we're talking about something in H as well as something in G. So what I want to do is think about, well, what does this look like? And the point is that theta is a one-to-one onto mapping. So therefore, there exists, let's say, an A and G such that theta of A is equal to x. So what I get here is that this is going to be x is just theta of A for some A. So I get theta of A times the identity. Why is that helpful? Well, notice now theta times theta. Well, theta respects the operation, so this is just theta of A times the identity. But what is A times the identity? Well, these are both in G, so anything in G times the identity in G is just the anything, so I get theta of A. But theta of A is equal to x, so I get x. So what have I shown is that x times theta of EG is just x. Now I'd have to do the other direction as well, but theta of EG times x is theta of EG times theta of A. Theta of EG times A is theta of A is also x. Therefore, theta of EG will act as an identity on H. Since the identity is unique for any group, that means that this is precisely equal to the identity on H. So whenever I have an isomorphism, it has to map an identity to an identity. Is that okay with everybody? All right. The next thing I want to show is that theta of A inverse is equal to theta of A inverse. So to start off with, I want to say, what does this even mean? Well, if theta of A inverse, this is an element in H. So that means theta of A is an element of H. So the inverse of that satisfies theta of A inverse is equal to the identity on H. Is equal to theta of A inverse times theta of A. So we have to do both directions, but if x inverse times x is equal to x times x inverse is the identity, that's the definition of inverse. So what I'm claiming here is that theta of A inverse is going to act like an identity on H. But what I do know is that A inverse times A is equal to A times A inverse is the identity in G, because A and A inverse are inverses. So I have to show that theta of A inverse satisfies this property. That is, if theta of A inverse times theta of A is theta of A times theta of A inverse is the identity, then theta of A inverse is theta of A inverse on the outside. So let's just take theta of A inverse times theta of A. Well, this is theta of A inverse times A is theta of the identity in G, but we just proved that the image of the identity in G is the image in H. So therefore, this times this, so x times y is the identity. And if I do the other direction, I get theta of A inverse is theta of A inverse is theta of E sub G is E sub H, which we proved before. So therefore, in both directions, this times this, x times y and y times x is the identity. So these two things are inverses. So this is the inverse of this. Therefore, we can say that theta of A inverse is theta of A inverse. So what does that mean? Taken as a whole is that, well, we already knew that Isomorphisms will respect multiplication, so we can do the multiplication before or after we're taking the image. But they'll also respect identities. So the image of an identity has to be an identity. They also respect inverses, so the image of an inverse is an inverse. So if we look at all the group properties, that was the products, the identities, and the inverses, any isomorphism will respect all of those. It'll always and send a product to the same product. It'll send the identity to the identity, and it'll send an inverse to an inverse. We also had the further note that if we generalize multiplication, so we do it over and over again, theta of a to the k is just theta of a to the k. So sometimes that'll help us when we have powers of things. So now we get that, okay, well, if we know we have an isomorphism, we know that these things are going to be true. We don't necessarily need to reprove them every single time. We just know that, okay, the image of this is that. And so we can use those as we're going ahead and doing more theorems. Such as, show that every cyclic group is isomorphic to Z or Z sub n for sub n. How in the world are we going to do that? That just seems crazy difficult. That is any cyclic group. Doesn't matter what I'm looking at. It has to be isomorphic to either Z or Z sub n. And I did actually mention this briefly when we were talking about cyclic groups, but now we can formally write up a proof of this or explain what this really means. Well, all right. So if we want to do a proof of this, what we have to do is we have to have a cyclic group, and we have to find an isomorphism from that group to Z. So let's just start off with the cyclic group. Was the group generated by A. And so if I recall, the group generated by A is the set of all A to the K such that K was in Z. So we did actually prove this, that the group generated by A is all multiples of A, so all the things of the form A to the K. All right. Now, suppose that each of these is different. So let's suppose A to the J is not equal to A to the I if I is not equal to J. So now that isn't necessarily the case for A to the K's. We even saw that when we looked at 1, 2, 3 composed with itself. So squared was 1, 3, 2. But this cubed was the identity. And this to the fourth would have been itself. So it's not necessarily true that all of them are distinct. But if all of them are distinct, what I get is that this set has infinitely many elements in it. And that none of them are the same, so none of them repeat. The reason why that's going to be important is because I have to find a mapping from here to the set of integers, or Z sub n, and I have to ensure that it is one-to-one and onto. And I'm going to need this to show that my next one is one-to-one. And so that is, I'm just going to let theta be a mapping from A to the set of integers. So because I'm going to have these are all different, I'm assuming I'm having infinitely many, so I'm going to have the set of integers. So I'm going to say this maps this as A to the K is mapped to K. And what I want to do is I want to show that that is a homomorphism. Now, why did I think to do that is, well, these are all the things of the form A to the K such that K is in Z, so why not just map A to the K and see what happens? I don't know if this is going to work out, it just seemed like a good idea. Well, I do know it's going to work out, but to begin with, I would not have known it's going to work out. I say, hey, that looks like a good idea. Let's try it. Let's see what happens. Let's see if this is indeed an isomorphism. First thing we want to do is make sure that it's well defined. So therefore, if I take something A to the K, so I have A to the K, is there exactly one K that this would be mapped to? So a to the 20 gets mapped to 20. A to the 30 gets mapped to 30. And so what I want to point out here is if any of these were equal, like a to the 10th was equal to a to the 20th, then notice what could happen is I could get a to the 10th and a to the 20th being mapped to both 10 and 20. So we would get that this is not well defined because if a to the 10th was equal to a to the 20th, then one element would be mapped to two spots. However, since we assume that none of these are equal, what I get is that a to the k is equal to k. Since a to the k is not equal to any of the other ones, then the only output for a to the k is going to be this 1k that we got for this version here. So this will be well defined because of this assumption. Is that all right with everybody? So there is a unique way to represent a to the k, which is just a to the k. So therefore, there is a unique number that it gets mapped to, or a unique integer in z. So this is a well-defined mapping. So what we would say here is note, if theta of A is equal to theta of B, then what we get is that this k would have to be this j, so therefore it'd be well defined. Alright, I'm sorry, I'm doing that backwards, but if a to the k is equal to a to the j, this implies that k is equal to j, hence theta of a to the k is equal to k is equal to j is equal to theta of a to the j. So that is, if I took two elements that were really the same, it would imply that the exponents had to be the same. Therefore, the image has to be the same no matter what way I look at it. So that is well defined. One-to-one. Assume theta of A is equal to theta, let's say, I'm already using A, so let's say theta B is equal to theta of C, while B is then equal to A to the K is equal to theta of A to the J, which implies that K is equal to J, which implies that A to the K is equal to A to the J, since these are the same exponent. So if the images are the same, then K is equal to J, which means the exponents are the same. Therefore, A to the K has to be equal to A to the J, so it will be one-to-one. Is it onto? Well, to show it's onto, we just show for every integer there exists an A to the K in this group. But for every integer there does exist an A to the K in this group. So this will be a well-defined one-to-one onto mapping. Alright, we're almost there. The last thing we need to do is show that it respects the operations. So what I want to do is let A to the K and A to the J be in the cyclic group generated by A. Then I have to show that theta of A to the K times theta, so plus, because we're using addition on integers, A to the J is equal to, eventually, theta of A to the K times theta, or times A to the J. So let's go ahead and do this. If I find theta of A to the K, that's just K. Theta of A to the J is just J. So it's just going to be K plus J. But theta of A to the K times A to the J is theta of A to the K plus J, because using exponent properties, A to the K times A to the J is A to the K plus J. Hence, theta of A to the K plus J is just K plus J. So therefore, if I add after, or if I multiply before, I'm going to end up at the same spot. So this will indeed be an isomorphism. Therefore, if none of the a sub j's are equal to a sub i's for any I not equal to j, we will get that the cyclic group generated by A has to be isomorphic to Z. Is that all right with everybody? all of our infinite cyclic groups will just be isomorphic to the set of integers. So if we're ever dealing with the infinite cyclic group, we don't have to think about what is that going to look like in general. We just say, well, what do the integers look like? Because they're going to look exactly the same. All right, just as a note, the other option is a to the j equals a to the I for some I not equal to j. So if they're all distinct, we get the set of integers. If they're not all distinct, we get some a to the j is equal to a to the I for some I not equal to j. So what in the world does that mean? Well, notice that if I multiply by negative j, this is an element of a, so a to the negative j times a to the j is a to the negative j times a to the I is a to the 0 is equal to a to the I minus j. Therefore, a to the 0 is equal to a to the I minus j, but e to the 0 is just the identity of the group. And I minus j will not be equal to 0 because I is not equal to j. So, what in the world does that mean? Well, it means if I have two things that are equal for some I not equal to j, well then a to the 0 has to be equal to a to the, let's say, k for some non-zero k. Now, if I is bigger than j, this is positive. But if j is bigger than I, then a to the negative I minus j is equal to a to the j minus I, but it's also equal to a to the negative a to the I minus j to the negative 1, which is equal to a to the 0 to the negative 1, which is a to the 0. Why in the world am I trying to do that is, if I combine this all together, what I get is that a to the 0 equals a to the k for some, well, let's use n, for some n in z and n strictly greater than 0. So the whole point of that was just if I had had a negative, I could multiply by negative 1. I still end up with a to the 0. So I get a to the 0 is equal to a to the n for some n greater than 0. All right. Actually, I want to use m if that's okay with you guys. M. Now, what I want to point out is that means that I have a0, a1, am, and these two are going to be equal. Is it possible that a to the 0 is equal to anything else for something smaller than m? Well, yeah. I know that something exists here, so this is equal to a to the 0. There might be other ones in here that are equal to a to the 0. But if I take all of these things that are equal to a to the 0, what we're going to get is a finite number of them. And so if I look at just the exponents will define a finite set of integers. So therefore, they must have a smallest non-zero element. So what I can do is I can assume that a to the 0 is equal to a to the n, but a to the 0 is not equal to a to the I for 0 less than I less than or equal to n. All right, let's recap. What I'm saying is that I know that a to the 0 is equal to a to the m. This might not be the only ones. There might be other ones that are smaller. But there has to be some smallest n. If there wasn't some smallest n, we could keep finding smaller and smaller ones, which would mean we'd have infinitely many elements here, which is not true. So there has to be a smallest n such that a to the 0 is equal to a to the n. So whatever that smallest one is, I'm just calling it n. So what I can say is a to the 0 is equal to a to the n, but for any I smaller than n, a to the 0 is not equal to a to the I for any 0 less than I less than or equal to n. getting somewhere, I promise. I'm getting sweaty up here is what I'm getting. All right, what I'm going to do is then I'm going to map theta from A to Z sub n given by A to the K maps to K. What I want to point out here is that this is distinct from the last one because my k's are only in Z sub n. So I'm not taking all integers. I'm only taking the integers from 0 to n minus 1. So if I'm mapping my a to the k's, I'm sending my a to the k to the k such that k is in n plus 1. Or, if I want to be more precise, what I really should say, I guess, is a to the k is going to k mod n. Let's say that. So I could have k for all integers, but I'm going to map it to k mod n. I think that's a better way of putting it. Then I know that the cyclic group generated by A consists of all the a to the k's. All the a to the k's are mapped to something inside Z sub n. So if I want to make this, or if I want to show that this is well defined, that actually takes some work like we did last time. So suppose that a to the k is equal to a to the j. Then I want to show that, well, let's use different letters. A to the I is equal to a to the j. Then what I have to show is that the image of a to the I is equal to the image of a to the j. And so the point here is that there are some a to the i's equal to a to the j's where I is not equal to j. But if a to the I is equal to a to the j, I have to show that a to the I as an image is equal to a to the j as an image. So what that really means is I have to show that I is congruent to j mod n. Because I'm sending a to the I to I mod n and a to the j to j mod n, so if I can show I is congruent to j mod n, that would mean it's a well-defined mapping. This proof is the first time we've actually had a hard time with well-defined, just checking to make sure it's correct, but we really do actually have to check it here. We have to assume that these two are equal. I have to show I is congruent to j mod n. All right. What I want to do here, so how am I going to do this is, well, what I do notice is that if I take a to the negative I times a to the I, a to the negative I times a to the j, I get a to the 0 is equal to a to the j minus I. Now, if, let's assume in this case j was bigger than I, then what I get is a to the 0 is equal to some positive number, j minus I. So, what does that mean? Well, let's suppose that j is not congruent to I mod n. Well, if I keep subtracting, I can subtract 2i, 3i, 4i, 5i, and I can use my division algorithm to get eventually this j minus I is going to end up somewhere between 0 is less than or equal to j minus some integer times I is less than n. Sorry. Let's write that a little bit differently. I was focusing on 2 there. I'm just going to focus on 1. I'm going to say a to the I is equal to, well, this is equal to a to the I times a to the 0, which is also a to the I times a to the n. But I can also multiply by a to the n again, because a to the n is e to the 0, is the identity, is a to the n. So this is a to the I plus 2n. And in general, what I'm going to get is a to the I is equal to a to the I plus any integer times n. All right. So what I want to point out here is that what I can do is I can take a to the j. If that's equal to a to the I, then it's equal to a to the I plus any integer times n. And so what I can do is multiply by a to the negative j, and I'm going to get more room here. A to the 0 is equal to a to the I minus j plus k times n for any integer k. All right. Now what I want to point out is that if I pick the appropriate k here, I can make this so that this number here is somewhere between 0 is less than or equal to I minus j plus k times n is less than n. Because I'm really just taking I minus j divided by n, so it's n times some integer plus the remainder. And so what I can do is I can force this to be in here. So what does that mean is, well, if this is not 0 when I end up in there, what ends up happening is that a to the 0 is equal to something where this something is less than n, which is a contradiction to the fact that n was the smallest such integer, such that a to the 0 is equal to a to the n. So therefore, what we have to have is that I minus j plus k to the n, when I get it in this range, has to be equal to 0. So that is I minus j plus k to the n is equal to 0 for some k. But what does that mean? Well, that means I is equal to j minus kn for some k. Hence, I is congruent to j mod n, because this is congruent to 0 mod n. So I is a multiple of n plus j. So these two are congruent mod n. Hence, if a to the I is equal to a to the j, I is congruent to j mod n. I know there was a lot going on there, and it wasn't the easiest thing to follow, but the point is that it does work out that if I have a to the I is equal to a to the j, then I has to be equal to j mod n. Therefore, the image is the same mod n. So this is a well-defined mapping. All right. Well-defined, 1-to-1 and onto. So to be onto, clearly we have all k for all integers, so we're definitely going to get the integers between 0 and n minus 1. So it's going to be an onto mapping. To be 1-to-1, let's assume that k is equal to j mod n, or let's suppose I is equal to j mod n. We have to show then that a to the I is congruent to a to the j, or is equal to a to the j. But if I is congruent to j mod n, a lot of the stuff we just did is then I is equal to j plus k times n for some k. Hence, a to the I is equal to a to the j plus kn is equal to a to the j times a to the kn is equal to a to the j times a to the n to the k, but a to the n is a to the 0, and the identity to the k is just the identity, so the identity times a to the j is a to the j. So if I is congruent to j mod n, then a to the I is congruent to a to the j. Your head hurts, T. I don't blame you. So anyway, I do want to point out that I have a The well-defined was kind of the hard one, so we had to show that if the images were equal, so a to the k and a to the j are both mapped to k mod n, then they had to be equal to each other in the original one. Once we got that, the onto was clear, the one-to-one took a little bit more work, but we just rewrote it like this, and we get, yes, a to the I is equal to a to the j. So this is indeed a one-to-one mapping. It's a well-defined mapping, and it's onto. So the last thing we have to do is show that it respects the multiplication. So if I take theta of a to the I times a to the j, I'm going to show this is equal to theta of a to the I plus theta of a to the j, where we're using addition mod n. Well, this is equal to theta of a to the I plus j is equal to I plus j mod n, and this is equal to I mod n plus j mod n. And since I mod n plus j mod n is just the same thing as I plus j mod n because mods respect the addition, we get that a to the I times a to the j, theta of that is theta to the I plus j is I plus j mod n is just I mod n plus j mod n is theta of a to the I plus theta of a to the j. So we do get that this also respects the operation. All right, let's recap, just because there's a lot that happened there. What did we show? Well, we showed that if I have that any two are the same, a to the I is equal to a to the j for some I not equal to j, then a to the 0, which is the identity, is equal to a to the m for some m. Therefore, it's equal to some n, where this is the least n, such that a to the 0 is equal to a to the n. If we map this, a to the k to k mod n, we noted that it was a well-defined one-to-one onto mapping that respected the operation. Hence, we have an isomorphism from a to z to the n. Therefore, what we get is that if none of the a to the i's are equal to a to the j's, we get the integers. We get isomorphic integers. If any two of them are equal, then we have to find the smallest one that equals. The smallest one that equals, we can find a mapping from here to z sub n. Therefore, all cyclic groups are either isomorphic to the set of integers, so all infinite cyclic groups are isomorphic to the set of integers, and all finite cyclic groups are isomorphic to z sub n for some n in the set of natural numbers. All right. I do want to point out, I know there's a lot that happened there. We're a couple minutes over, but I started a couple minutes late, so that's okay. There was a lot that happened in that proof, and if you didn't follow all of it, that's quite all right. I actually have this one already written up on the website as well. It's titled something about the cyclic groups, representations of cyclic groups. I think that's the title. So if you want to see this written out in much more detail, that's all available to you on the website. So you can kind of read that as you're going through and watching this, and put together, you can get a good understanding of what's going on. So, feel smarter and dumber at the same time. Good. That is the goal, isn't it? I told you guys that before. As you become more educated, you tend to realize that you tend to learn more about what you don't know than you do know. So you do tend to feel both more and less intelligent at the same time. But yes, T, I would suggest reviewing the video later, but bring up the website at the same time so you can read along with it, and that'll really help out. The chalkboard's just really small. It's hard to keep all of the information up there so I can refer back and forth, but the write-up, I don't have that problem. So I would suggest you guys doing that. And this is a really interesting result. Why is it such an interesting result? Is that it's actually telling me a lot of information. Any cyclic group, no matter what I'm talking about, if I'm talking about compositions of mappings, if I'm talking about adding or multiplication or some types of symmetries or anything, no matter what it is, any elements, I can always rewrite them with a renaming so that it looks just like either the set of integers or z sub n. So if I want to think about cyclic groups, I don't have to think about all of the various infinite different ways I can write cyclic groups. All I have to do is think about what do the integers look like and what do the integers mod n look like. And that's the power of this, is that it is a representation theorem. So I can focus on a concrete example instead of having to look at a generalized abstract example of cyclic groups. As a note, we will try to do more of that in the next chapter. And so instead of just looking at cyclic groups, we'll actually look at all groups. And we'll say, can we represent all groups in some way so that we have a concrete way to look at them instead of having an abstract idea to think about. With that said, thank you guys for joining me. You do have your test due tonight, so make sure to get that in by midnight on Blackboard. If you guys have any questions, feel free to ask either here or just send me something in Discord or an email. I may not answer, but I will try to give you the best answer I can. So feel free to ask. And otherwise, I hope it's going well. Good luck with all of that. And I will see you guys on Monday.